Okay, the next thing we're going to do is kind of a chemistry review. And the reason I'm saying kind of is we haven't done lipids yet, and we'll go there next. But I usually end up putting this in here because it seems like a good point to really make sure you're solid on differentiating a fat from a carb from a protein. And it's also a point at which I've been kind of explaining a couple things like functional groups on the spot, but not really getting into them enough to give you a chance to really use the material. So because of that, this kind of fits here, even though it's kind of a review and kind of not a review. So we'll do it. Okay, so we're looking at organic molecules, and we've pretty well introduced that. We're going to have carbon, hydrogen, oxygen, we'll have some nitrogen, we'll have some phosphorus, we'll have some other things. We've talked about organics before, and you've talked about them a lot in other classes and everything. So we'll primarily be focusing on our fats, our carbs, and our proteins. We'll have some nucleic acids in a conversation we'll have more later next term. We'll throw in some vitamins and minerals along the way, which are not organic, but they'll mix in with our organics. You did the periodic table in general chemistry, so I won't put you through that again. We're going to look at the chemical properties of carbon, and I know you've done that. You've distributed electrons in shells and looked at whether the outer shell was full or not full. But based on that, carbon has 4 attachment points, so we'll definitely use that. Carbon bonds to other carbons, so we'll absolutely be doing that. Might be in chains, might be branch chains, might be rings. We're also going to have the carbon bonded to other elements: hydrogen, nitrogen, oxygen, sulfur, phosphorus, other things like that. There's different ways of drawing our molecules, and I know you did that in general chemistry, so we won't go through doing that again, but we will talk about it a little bit. So what we're going to talk about is hydrocarbons. Hydrocarbons, and we're going to talk about some naming. So if it's a hydrocarbon chain and there's no double bonds in it, so it's all single bonds, we call that saturated, and that'll get important in fatty acids. It's called an alkane, and we're going to use that end part, ane, when we're doing some naming shortly. If we have double bonds in there, it's going to be unsaturated. Again, gets important with fatty acids. It's going to be an alkene. Triple bonds are an alkyne. We're not really going to use that. And we'll have a couple of aromatics, but alkane and alkene are going to be our 2 big ones. All right, let's talk about functional groups. And functional groups is one of the big reasons that I rearranged the PowerPoints a little bit, or the topics a little bit, and kind of do a chem review before we have anything or have the completeness to review. So, functional groups, like we said, are a way of naming part of a molecule, a certain arrangement of atoms in one part of a molecule. Rather than saying we have this bonded to this over and over, we give it a name and call it a functional group and give it a name. So the first one is an alcohol. Don't forget R is our variable, like X in math. So we have whatever the rest of the molecule is, then an oxygen attached and a hydrogen attached. When we have that, of course, very often we just write OH. We don't show the bond in the middle. That's an alcohol. So we can put a beginning on it, like methanol, ethanol, whatever. So it'll end in the OL for alcohol. All right, the next one's an ether. So this time we have something bonded to an oxygen, bonded to something else. So instead of that terminal hydrogen, we have something else. We could also go R and R1, another R. Very often we're going to have an ether linkage between two monosaccharides. So we'll have, say, a glucose, let's make sucrose, with an ether linkage, to a fructose. And that would make the two monosaccharides a disaccharide like we just talked about. When it's an ether linkage joining two monosaccharides, it's still an ether, but we also often call that glycosidic. Again, remember when we said we're in the context of carbohydrates, we're going to be GLU or GLY very often. Convenient for a little bit until it just turns into way too many. All right, the next one is a carboxylic acid. We saw that in our amino acids. Or we had an amino acid, we had NH2 on the end, carbon, our R group, hydrogen, and a carboxylic acid. That's what made it an amino acid. So we looked at this one. Spelled out completely, we'll do an R group. Carbon double bonded to one oxygen, single bonded to another, single bonded to a hydrogen. And of course, we know very often we'll just write COOH, even though those oxygens aren't attached to each other at all. So that's our carboxylic acid. Next one's an ester. And if you notice, we're kind of drawing something and then switching a hydrogen out for another R group. An ester is my R group, carbon, double bonded to an oxygen, single bonded to another, single bonded to another R group. So this is my ester. We could see them in a lot of different places, but very often we're going to see them in the context of lipids. When we make a triglyceride, we're going to use an ester bond to do that. The other thing we're going to do is we're going to kind of practice, in a way, terminology. And here's why. When we're doing carbohydrates, we're going to do a test on carbohydrates, and you know your questions will be on carbohydrates. When we do proteins, we'll do questions on proteins, and your test will be on proteins. Same thing with lipids. Then you're going to get into the final next term, or boards, and you'll get a question that you look at it, and it might be fats, might be carbs, might be proteins, and how do I know that? Like, let's say, I don't know, one I like doing on the final, we'll talk about it so you'll be prepared before we do it. But I'll say you ate a ham sandwich. And of course you had your bread and your ham, and you had, I don't know, processed American cheese food slices and some mayo. So we've covered everything there. We have carbs in the bread, fat in the fake cheese and mayo, protein in the ham. What are you asking me about? You asking me about the fats, the carbs, or the protein. So we're going to have some terminology to help you out with that. If you see GLY, GLU, you're going to get your brain on carbs. If you see lip anything, acyl or acetyl anything, or ester anything, you're going to get your brain on lipids. And we'll practice this. Don't worry about it much now. But my point now is, we might have an ester bond in more than one place, but if we make a point of calling it out, we're probably in the context of lipids. With proteins, amino acids, AM or PEP are prefixes you're going to see on a lot of stuff. Maybe prot, like protease and things like that. So we're going to practice what word points your brain in whatever direction you need to be pointed in. So anyway, that's that. Last two we've got to do on this slide are aldehydes and ketones. So we talked about them a little bit with carbs. So my aldehyde is a carbon double bonded to an oxygen, single bonded to a hydrogen. And we saw that turned into an aldose, an aldehyde alcohol. Same idea, I replaced the hydrogen with something else. Carbon double bonded to an oxygen, single bonded to another R group is my ketone. So make it a sugar, could be a ketose, and so on. So I would know these, and again, we made the point of this is a terminal and this isn't. I would know these, and they're absolutely fair game to ask you. And a little bit of a story. When I came back to chiropractic college and they made me take biochemistry, I thought, functional groups have been a while, but I know all my tests are going to be multiple choice. We also had this deal where they're not going to draw anything and make me name it. They're not going to name anything and make me draw it. They can't ask me functional groups. No problem. I don't feel like reviewing them. I'll get to that later. I was so wrong. So let me tell you how functional groups get asked in multiple choice. You'll get things like, which of the following functional groups, contains a nitrogen? Of course, that's your amino group. All of the following functional groups have a carbon double bonded to an oxygen except, so aldehyde ketone have it, carboxylic acid ester have it, your except has to be something else. So the way I would handle it would be, you get your list of functional groups and you're asked which one has or doesn't have, draw the 4 functional groups. Then just look which one has or doesn't have whatever you're getting asked about. The reason I'm being so explicit with here's how you're going to get asked, I want you to be really, really solid on these. And it's not about testing. I don't care about testing. I just want you to know this stuff and be able to use it, apply it, and be really fantastic chiropractors taking really, really good care of your patients. So, tests are just necessary evil on the way to that. So, the reason I care so much about you knowing these is particularly next trimester when we're talking about reactions. We'll say things like, we break the ether bond. And if you don't immediately know what the ether bond is to know what we broke, you're going to lose the rest of the conversation. Or because it's a ketone, this happens. If you're busy Googling ketone, you're really losing the rest of the conversation. So really important that you know these and know them well enough that when we're talking about them, you'll say, oh yeah, that's a carbon double bonded to an oxygen and whatever. Okay, a few more drawn better than I probably just drew them. Actually, not more, just drawn better. Okay, so both aldehydes and ketones have that carbon double bonded to an oxygen, and we did this in the carbohydrate intro. Glucose is an aldehyde alcohol carbohydrate, so because of that hydrogen, that part's sticking out, it's on the end. Fructose is a ketone, so it can be in the middle of the molecule. Glucose is a 6-carbon monosaccharide in a 6-membered ring. So remember, 1 carbon sticking out and an oxygen is a member of the ring. Fructose is a 6-carbon molecule with a 5-membered ring. We have 2 carbons sticking out and 1 oxygen in the ring. We can convert carbs to alcohol, and we'll talk about that. We'll talk about sugar buzzes and stuff like that when we start processing our carbohydrates. Okay, isomers. We've talked about this a little bit, but can't hurt to hit it more times. Same components, different arrangement. And again, function follows structure, so the arrangement gets really, really important. The isomers, even though they have the same components, can have different properties. Most common isomers are cis and trans. So we talked about this a little bit too, but let's do it again. The more we hit this stuff, the more it gets driven into your head. If whatever we're talking about, the functional groups or whatever, are across from each other. Call that the trans isomer. If they're adjacent to each other, we call that the cis isomer. In most stuff, trans is the more stable. Most of the time, not all. Your exception is going to be fatty acids. And I bring this up over and over because this is where the organic chemists get messed up. You guys just go for trans. You like your molecules on the trans configuration, forgetting that fatty acids are actually bent, so they're more stable in the cis configuration. Of course, what do you typically get asked about? The exception, right? Chiral carbons we just talked about. The D form sends plane polarized light to the right, dextrorotatory. L form to the left, levorotatory. We need a chiral carbon to have a D and an L form. So our D form is the naturally occurring form of a sugar or a carbohydrate. And again, I'm going to keep going back and forth, sugar or carbohydrate. So D something, Os, is our naturally occurring form of a carb, a sugar. Amino acids are going to be a little bit different. Okay, next thing we're going to talk about is amines and amides, a little bit. These are functional groups containing nitrogen. So when you see nitrogen, you're going to think an am on the front of it. Amine, amide, amino. So we're going to have the amines and amino acids and alkaloids, derivatives of ammonia. Amides have peptide bonds. They have a carbonyl group adjacent to the ammonia. And we'll come back to a lot of these. So an amine starts out as an ammonia, NH3. So I've got NH3. I replace one of my H's with something, primary amine. I replace my second H, hydrogen, with something, secondary. Third one, tertiary. So NH3, 3 hydrogens, replace 1. I make a primary amine. 2, I make a secondary. 3, I make a tertiary. We talked about amino acids. We have a carbon in the middle. We have an R group. And again, the R group is what makes that amino acid that amino acid. I have a hydrogen. I have my carboxylic acid. And I have my amino group. Conventionally, we tend to put the amino on the left, the carboxylic acid on the right. There's no science-based reason for that. Convention more than anything. A little bit better molecule than I probably just drew. Amino acids occur as the L form. So a lot of your amino acids are going to end in ene, and we're going to talk about the particular ones and their particular properties based on their R groups. So I can have alanine, just a little methyl group is my R group, and I can have an L or a D form. The naturally occurring one for amino acids is the L form. So L something ene. And again, sometimes they won't end in ene, but it's a good indication. So here, be a little careful. I'll hear you guys sometimes saying, well, the naturally occurring form is L, we need to buy L. And what you're referring to buying is supplements. So yeah, if you're supplementing your amino acids, you're going to buy the L form to supplement with. You want to supplement, with the naturally occurring form so you can absorb it and whatever. You don't supplement sugar. If we could unsupplement, desupplement, I don't know, is that a word? Sugar, we'd probably be in better shape. So be a little careful with that. Just contextually, you can cause some confusion. So naturally occurring form of an amino acid is your L, your levorotatory. So of course that's the one you might be supplementing. Naturally occurring form of a carbohydrate is still going to be the D form. You're just never, ever going to supplement that. Okay, so our amides are kind of like an amino acid without the carboxyl group. We take the OH off the end of the acid and put something else there. Talked a little bit about oxygen being the big electron hog and the result of that. Can't get charged because of that in this case. So we'll come back to these. Okay, let's talk about fatty acids. And I should have put a slide in here. Fatty acids are based on alkanes if they're saturated fatty acids. So what a fatty acid is a chain of carbons, however many, with a carboxylic acid on the end. And I can have my hydrogens and everything. And if I have all single bonds, we call that saturated. So think of it as saturated in hydrogen. I have no double bonds left that I can open up and add another hydrogen. A little bit of, I don't know if I should say context or weirdness or what. When I'm saying there are no double bonds, it's all single bonds, I'm referring to from here over. This one doesn't count. This is part of the carboxylic acid. So we'll say we have no double bonds, we have all single bonds, whatever. And sometimes when you're learning this, you'll say, well, no, hang on, this one here doesn't count. Got to be in the chain, not the carboxylic acid. So it's saturated if I have no double bonds in that chain part. When we get going a little bit with this material, well, and really next and a lot of this trimester is setting up for next trimester. But next trimester, what you're going to see is this chain of carbons, just by nature of being a chain of carbons in a fatty acid, contains lots and lots of energy, lots and lots of calories, if you want to say it that way. Calories are just a unit of energy, as in how many ATP, kilojoules, whatever. So this chain is going to contain a whole bunch of energy. That's why fats is such a good storage molecule. Okay, carbs and fats are related because we convert the carbs to fats. Eat too many carbs, you're going to make fat, you're going to get fat. Let's get up. I've unsaturated somewhere. All right, we'll come to that. All right, so anyway, let's talk about nomenclature a little bit. And for here, we'll just say here, I have it set up for alkanes. So what I really want you to get out of it is the prefixes. So meth is 1 carbon. F is 2 carbons. Prop is 3. Bute is 4. Pent is 5. Hex is 6. Hept is 7. Oct 8. Non 9. Dec 10. Probably don't need it yet, but for the sake of your notes. Icoses 20. So let me write 20 there. So we can use this, and we are going to in a few minutes, but we'll do it now. So let's say I have 3 carbons in an alkane. I'm going to call that propane. So it's 3 carbons with all hydrogens on it. That's propane. Let's say I have 5 carbons and a double bond. So if I have 5, there's my pent. If I didn't have any double bonds anywhere, it'd just be pentane. If I have a double bond somewhere, pentane is going to become pentene. And then I have my carbon or my hydrogens on there. Some of you guys who have done organic chemistry, you would know that this is 2-pentene because I have the double bond on carbon 2 and so on. So that's my just straight out ane and ene for alkanes and alkenes. If I have ene, you know there's a double bond in there. If I just have ane on the end, you know this knot. So we're going to build that in a minute into fatty acids. Okay, so we said fatty acids are based on alkanes, kind of. Saturated fatty acids are based on alkanes. Well, let's just do this. So let's pick one, because I want to get into the ending with this. Let's say, I don't know, I'll do 6 carbons. Of course, my last one is COOH, my carboxylic acid. That double bond doesn't count. So when I say I have no double bonds in here, I'm legal saying I have no double bonds in here, because this one doesn't count. It's part of the carboxylic acid. I have no double bonds in the main part of the chain. So fatty acids end in oic acid. So we're going to build the name of this fatty acid up. So it has 3 parts. First part's going to be the number of carbons. I should have drawn this over a little bit. I'm going to take a second to move it over. Maybe a long second. Okay, what do we have? 6? We'll say 6, I don't remember. Short memory. All right, so like we said, this double bond doesn't count. This is my carboxylic acid. But I'm going to name this. So I've got parts to my name. So first part of my name is going to be the number of carbons. So what do I have? 1, 2, 3, 4, 5, 6. This carbon counts in my count. So it's going to be 6. So this is number of carbons. Next part of my name is going to depend on whether it's an alkane or an alkene. I have no double bonds, so it's an alkane. So it's going to be hexane. So this is based on an alkane. And there's no space in between. I just left a little one so you can see what I'm doing, where I'm getting the parts. So then it's fatty acid. It's a chain of carbons with a carboxylic acid on the end. So it's going to be hexanoic acid. There is a space between oic and acid. So this just means it's a fatty acid. So it's hexanoic acid. If we're saying it, if we're verbally expressing fatty acid names, it's hard sometimes to pick up on whether it's based on an alkane or an alkene, especially if we say it quickly. But here, that "an" means alkane, but we might say hexanoic acid, hexanoic acid, and really not a detectable difference in it. So anyway, that's our alkane. That's our saturated fatty acid. Okay, so unsaturated fatty acids are based on alkenes. So let's draw one. Let's do 6 again. Let's do hex. I don't have a lot of room, but that's okay. We'll put it in here. And I'll throw my double bond in. And I'm making this up. I'm just throwing carbons. We're just throwing carbons around. All right, so let's say this was our fatty acid. So again, this double bond doesn't count in anything, but we do still have another double bond. So first thing is going to be how many carbons? 1, 2, 3, 4, 5, 6. Hex. Is it based on an alkane or an alkene? Do I have a double bond in there? Yes. So hexane. What is the molecule? The molecule is a fatty acid. So hexanoic acid. So again, saying it, sometimes it's not detectable, whether it's hexane or hexene, but written, obviously it is. So number of carbons based on an alkene, and it's a fatty acid. Okay, so we got a deal. We said, I'm not going to name anything and make you draw it. I'm not going to draw anything and make you name it. None of that organic chemistry stuff. Why are we doing this then? Well, here's why. You're going to be reading. Again, whatever your interest is, go read about it. I know you don't have an awful lot of time, but when you do, go read about it. And you would be reading, and you'd come across a fatty acid and blah, 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 oic acid. Well, I wonder what that means. You would go the other way with this, like we do with so much of our stuff. You're breaking it down the other way. You would say, okay, oic acid, we're talking about a fatty acid here. Aniran, we're talking about a saturated or an unsaturated. Of course, this one is unsaturated. Remember, when we saturate in hydrogen. So we're talking about an unsaturated. Oh, hex, 6 carbons in my unsaturated. So you'd be backing it out that way, and then your conversation, whatever you're reading, would continue. It's like, oh, that's why that's doing whatever it's doing or whatever. So when you're actually using it, we're doing it now a little bit academic exercisey, but when you're actually using it, you're going to be going the other way with it, kind of translating it to what's really going on with the structure. So again, with fatty acids, unsaturated fatty acids, the cis configuration is the naturally occurring. This is the exception to the rule, you organic chemists. And of course, what do you typically get asked, the rule or the exception? Well, you know the answer to that. So cis is our naturally occurring form, and we're actually bending the molecule to make that work. So we have a double bond somewhere, that's what makes it unsaturated. Our an becomes ene, or anoic. There's not many naturally occurring trans fatty acids, and that turns into a whole thing nutritionally. So Dr. Krabbe will talk about that in the nutrition class. There's a lot of physiological implications to eating those trans fatty acids. Okay, fatty acids are organic acids with a long carbon chain. This long carbon chain is going to be a big deal. The long carbon chain is lots of energy tied up in that long carbon chain. All those carbons contain energy, contain calories. So fatty acids are going to become, well, not become, but our conversation will evolve in the direction of them being big storage molecules. So we had that carbohydrate, glycogen, that's our short-term storage. Fatty acids are our long-term storage. So if we eat and keep eating and fill up our glycogen and keep eating, we're going to make fatty acids. Once we make 3 fatty acids, we're going to make a triglyceride, and that's our transport mechanism for fatty acids. And actually, let's talk about triglycerides for a second here. So, and we're going to talk about them later, but I'm not sure where exactly they are. So let's do it now so you have it. When I want to make a triglyceride or a triacylglycerol, I start out with a molecule of glycerol, the 3-carbon alcohol. So here's the tri thing coming in. And I actually converted to glycerol 3-phosphate, but we'll talk about that. But what I'm going to do is I'm going to take this 3-carbon alcohol and I'm going to attach 3 fatty acids to it. Carbon 1 will be a saturated, carbon 2 will be an unsaturated, carbon 3 will be either or. And we'll come back and talk about that. But what I'm going to form in between is ester bonds. So all in between here. So what I'll have is I'll have that 3-carbon molecule. Actually, we could use this. Let's line this up better. I'll have that 3-carbon alcohol with these big chain molecules attached to it. So what I have at that point is a molecule that contains lots and lots of energy. So I've got these carbon chains attached to the 3 carbons tied up in one molecule. That's my triglyceride, triacylglycerol, or my TAG. That will go through my bloodstream to deposit some of these fatty acids, fats, to tissues, typically adipose tissue, muscle, places like that. And we'll talk about it later. But the cool part of this molecule is these chains. It's just energy and energy and energy. So it's a very energy-rich molecule, I guess is the best way of saying it. So we're going to make these. We'll go through the steps and the reactions and the process to make them. And we'll talk about transporting them. Little out of order, we're going to transport them first. We'll transport them this trimester. Then we're going to make them next try. But I'll attach the video again next try, so after you've made them, it'll feel a little more relevant. You can go back and talk about transporting them again. Okay, the cis configuration is the naturally occurring in fatty acids. Trans is the naturally occurring in everything else. In nutrition, you're going to talk about the ramifications of eating too many trans fats. You'll also talk about food labeling a little bit. And again, like we mentioned before, if you want to talk about food labeling in a patient education seminar, patients typically really like it because there's so many things that they just don't know and so many things that aren't as they appear. Like one is, if you have less than half a gram of trans fats per serving in food, you can call it 0 grams of trans fats. Well, the per serving part is kind of the key to that. You can do stuff like, I don't know, make your serving 2 potato chips or whatever. You know, who eats 2 potato chips? But then if that's the serving size, call it 0 grams trans fats. So again, you have to be aware of things like that to properly read a food label and know what's really going on. Okay, so we said the carboxylic acid on the end of the alkane or the alkene makes it a fatty acid. A couple more functional groups. I think we've hit all of them. Sulfhydryl we haven't. That's okay though. Okay, what we're really going to be doing next trimester is oxidizing carbon-containing molecules. And this is where the functional group idea gets so important. And just in the sense of, if you're not really solid on it, it's really easy to lose the rest of a conversation. So we're going to be going from, we'll take whatever molecule, and we'll say you ate this fat, this carb, this protein, and here are the steps, reactions, processes you're going to go through and do to make a consistent, available supply of ATP for your cells. But as we're doing that, we'll say, well, we just changed this alkane to an alcohol, to an aldehyde, to a carboxylic acid, and so on. And if you're sitting there Googling carboxylic acid, you're losing way too much of the conversation at that point. So that's why it's super important that you know these. Okay, we're going to talk about bonds, and we've done this conversation. You've done it in general chemistry, so I won't spend a bunch of time on it. But we're going to have covalent bonds that we're going to make and break sometimes. We're going to have some intramolecular forces. We'll get into those here and there. We're going to talk about cell membranes next module, so we'll get into hydrophilic, hydrophobic interactions there. Talk about ionic interactions a little bit. Hydrogen bonds are going to be huge. They're not a particularly strong bond typically, but they're a major strength in numbers kind of story typically. Bond polarity comes into it. We've talked about this. Bond polarity gives us our partial charges. It gives us the opportunity to have hydrogen bonds. Hydrogen bonds, like we said, are huge. We have certain molecules, most often oxygens, that are big electron hogs, hogging from something else, leaving these partial charges that allows us to have this interaction. When we're saying, why is this molecule strong, whatever, typically, most frequently, the answer is going to be hydrogen bonds. Okay, that's it for our chem review. I know it was kind of review, kind of not. It was just kind of the best place for it, because I wanted to get the functional group story out of the way, and I wanted to get some of the naming. I wanted to get the fatty acids introduced a little bit. So we'll stop there with that. Next place we're going to go is to our lipids, one of which will be fatty acids. So we'll get into some more naming with those and some more of what we're going to do with those.